Investigation of frictional and fluid flow losses. In this experiment, we designed a homemade turbine system to investigate how pipe friction varies with pipe length and how that ultimately affects both the kinetic energy of water at the outlet and the rotational kinetic energy of a turbine. The goal was to visualize how friction inside a pipe gradually eats away at the energy the fluid carries, meaning as we make the pipe longer, we expect less energy reaching the turbine and a slower rotation rate. What you see on the top right corner is a complete setup consisting of a simply gravity-fed system designed to make this relationship visible and measurable using basic tools and materials.
Apparatus: a bottle for filling or emptying water. A 5-liter transparent plastic bottle positioned approximately 1.2 meters above the ground and kept constant. A flexible transparent plastic pipe of original length 2.7 meters and internal diameter 5 millimeters was used. Two phones, one used as a camera to record revolutions of the turbine and one used as a stopwatch. Craft knife to cut bottles, pipe, and glue. Small water turbine connected to the outlet of the pipe. A plastic container placed on the ground to collect outflow water. The key idea was to build a compact gravity-driven flow rig that could easily be modified.
For the water reservoir, the top of the 5-liter bottle is cut to create an open filling point. This is done to ease the filling process and fully expose the free surface to the atmosphere, as well as to ensure constant pressure. The pipe is attached to the bottom of the reservoir, where a small hole is cut using glue and tape to prevent leakage during fluid flow. The collection tank is a 5-liter bottle cut horizontally and placed on the ground, where the turbine will be placed. Ice cream sticks and bottle caps were utilized to make the turbine wheel. The turbine is then attached to the collection tank, where the stores are attached on the other ends to reduce rotational friction. The end of the attached pipe is placed right above the turbine, where the minimal distance is required in order to use water velocity at the pipe outlet for experimental calculations.
The pipe should be measured and cut to an initial length of 2.7 meters from the entry point at the reservoir to the exit point for the first set of readings. This was done using a 1.5 meter measuring tape with a resolution of 0.5 millimeter. A small amount of water should be in the reservoir. The pipe should be held below the reservoir height so that some water can flow through, removing any air bubbles. Also ensure that there are no leaks in the setup. The 4-liter mark should be carefully measured out and marked beforehand, and the reservoir should be topped up with water to this mark. This should be done after the experiment is carried out each time to replace the water that was used. This should also be observed with the water level being at eye level to avoid any inaccuracies. The turbine wheel should be set such that the red marked arm of the turbine is vertically upwards. The turbine should be reported throughout the duration of the experimental procedure. This reporting will later be slowed down to count the number of revolutions for a given time frame in order to determine angular velocity. The water should be released as the timer starts. The reservoir water level must be carefully monitored. The water flow and stopwatch should be stopped as soon as 1 liter of water has been drained from the reservoir and the 3-liter mark has been reached. The time should then be recorded. The reservoir should be refilled and the procedure repeated, twice for every pipe length, so that the averages can be taken to improve accuracy and identify any outliers. 30 centimeters should be measured from the exit side of the pipe. The pipe should then be cut at this point. The last time that the experiment is carried out, the pipe should be at a length of 60 centimeters from the inlet to the exit point, making a total of 8 pipe lengths and 16 sets of readings. Take caution when using the craft knife to cut the pipe to avoid any injuries.
To evaluate the collected data, the first key calculation was the exit velocity, which was calculated using the first listed formula, where Q is the flow rate determined by dividing the measured volume with time taken. Next, We compute the head loss using Bernoulli's principle and the Darcy-Weisbach equation, where h is the reservoir head of 1.2 meters and v is the calculated exit velocity. Furthermore, the kinetic energy of the water at the pipe outlet is calculated with the formula where v collected is the 1 liter of the water discharged. Kinetic energy of the turbine was computed using the measured angular velocity of the turbine, and the area moment of inertia was calculated about the centroid of the turbine. Finally, MATLAB was used to automate these calculations for all pipe lengths and to plot the graphs comparing theoretical and experimental results.
Several key fluid mechanics principles were applied in this experiment. Continuity principle states that the flow rate through the pipe equals the discharge from the reservoir. Bernoulli's principle states that the gravitational potential energy from the elevated reservoir converts into kinetic energy, but part of it is lost due to friction and fittings. Darcy-Weisbach equation states that head loss due to friction is directly proportional to pipe length. Reynolds number is used to check flow regime, with our setup mostly operated in the transient turbulent range. The transient draining, even though the water level dropped slightly, each 1 liter run was treated as quasi-steady, meaning the head change was small enough to assume constant head.
In conclusion, this experiment successfully demonstrated the link between pipe friction and energy loss in a simple fluid system. The experiment also showed how frictional losses reduced the usable kinetic energy reaching a turbine. Future improvements could include adding a flow meter, accounting for minor losses, and using a more precise turbine to capture efficiency more accurately. Overall, the experiment effectively connected fundamental theory with the practical and visual demonstration of how energy dissipates into a fluid flow.